Hello everyone. So, I continue with the problem of heteroscedasticity in module 18 of the course on econometric modeling. In module 17, we discussed the definition of heteroscedasticity, what kind of problem it leads to, and then how we can test for heteroscedasticity. There I had discussed 4 alternative tests to test for the presence of heteroscedasticity, and they were the Spearman rank correlation coefficient test, we discussed Goldfeld quant test, then we discussed Brosh-Pagan test, and finally the White's test. Now, I am going to discuss how to deal with heteroscedasticity. Now, dealing with heteroscedasticity has actually two different aspects. So, when we study, as I have mentioned in the previous module, that there is something called autoregressive conditional heteroscedastic errors. So, in those situations the heteroscedasticity is actually modeled, or the heteroscedastic errors are incorporated into the models instead of trying to remove the problem of heteroscedasticity. But here currently what we try to do is primarily while dealing with heteroscedastic errors, we try to remove the problem of heteroscedasticity. By removing the problem of heteroscedasticity, what we obtain is, we certainly of course the efficient estimators, but we are not actually sure about whether they are unbiased or consistent or not. So, most often they will not be unbiased estimators, but they are certainly best estimators, that is the most efficient estimators. So, if the form of heteroscedasticity is known, which is actually our trouble many times, then an alternative estimation method which takes this into account can be used. One such possibility is called the generalized least square or GLS method. GLS can be viewed as ordinary least square technique or method applied to transformed data that satisfy the WLS assumptions. So, whenever we transform or modify the data so that the data fulfills the basic assumptions of OLS or CLRM assumptions or Gauss Markov theory assumptions, then that is called GLS or generalized least square. Suppose the true relationship is given by this, where this x contains all the independent variables for observation I. So, observation, this is for a single observation. So, if you remember, our x was an n by k matrix where there were n observation. So, going by that, this x actually will have only one observation and of course k independent variables. So, given that my beta 1 will be a k by 1 vector, then my x is a 1 by k vector, and plus we have u I, where x I contains all the independent variables from observation I. Let the standard deviation of the disturbance term in observation I be sigma u I. So, instead of having the same dispersion or variance across all the observations, we are having now observant specific standard error or standard deviation, which is denoted by sigma u I. If we know sigma u I for each observation, we can eliminate the heteroscedasticity by dividing each observation by its value sigma, its value of sigma. So, what happens is that this is the ith observation, and for the ith observation the standard deviation of the error term is sigma u I, right. So, I am dividing the ith observation by the population error standard deviation, which is sigma u I. So, instead of y I equals beta naught plus beta 1 x I plus u I, now I have u I divided by sigma u I equals to beta naught plus sigma u I plus beta 1 x I divided by sigma u I, and then finally u I upon sigma u I. The disturbance term u I upon sigma u I is homoscedastic, because the population variance of u I sigma u I is expected value of u I divided by sigma u I whole square. Then sigma u I being specific or constant, now of course specific to the observation I, but then the variance is actually a constant term. So, it comes out as 1 upon sigma ui square, and we have expected value of ui square in the multiplied to 1 upon sigma ui square, and then this is equal to sigma ui square. Finally, sigma ui square cancels out and we have 1. So, the variance of ui divided by sigma ui square is actually a constant, and that is equal to 1. Therefore, every observation will have a disturbance term drawn from a distribution with population variance 1, and the model will be homoscedastic. Note that there is no constant term as corresponding to beta naught. There is a new variable which is 1 upon sigma ui for the ith observation. So far for all the observations we had one constant term, that was 1, and corresponding to that constant term our parameter was beta naught and estimated parameter was beta naught hat. But now what I am having is 1 upon sigma ui, right, because corresponding to this expression my parameter is beta naught and variable is, instead of 1, my variable is sigma ui. Now, sigma ui is an observation specific variable, right, and as a result of which we do not have any constant term. However, we obtain efficient estimates of beta naught and beta 1 with unbiased standard errors, because you can see that since we are now having homoscedastic variance, our estimates are now efficient, and the standard errors are actually unbiased estimators of the population standard deviation. The GLS estimators for correcting heteroscedasticity are called weighted least square estimators. So, GLS can be applied in varied situations or in various circumstances. Now, when we use them for correcting heteroscedasticity, then they are specifically called weighted least square estimators. So, GLS or WLS is actually one kind of GLS. Under WLS, the form of heteroscedasticity is specified and WLS method is applied. If the form specified is correct, then WLS is more efficient than OLS. Of course, specifying the form correctly is actually not an easy thing, but if we can specify the form, then as I have just explained that WLS becomes more efficient. So, the previous example also is an example of WLS only, but in a more generalized context. Now, we are becoming more specific by bringing in the definition of WLS. Suppose variance of u given x is equals to sigma square hx, where hx is some function of x. So, instead of writing sigma I or sigma square ui, I am now specifying the functional form, and in that functional form we have a constant component which is sigma square and a component which is dependent on the independent variables which is given by x. Now, again I am still not specifying the functional form of the independent variables. It is just that the sigma ui square or sigma I square has been segregated by taking out a constant component denoted by sigma square and leaving the rest as dependent on the independent variable. Now, since variance of ux is always positive, hx greater than 0 must hold, because if hx is not greater than 0, it is a negative number, then the variance of ux will also be a negative number, but that is not possible because variances are always calculated on the basis of squared sum. So, squared sum of the deviations of the individual values from its mean, and as a result of which they can never be negative numbers. Suppose the function hx is known such that sigma I square equals sigma square hxi equals to sigma square hi. So, the form of hxi is generally written as hi, and we take an example to show what kind of form hi can take. For example, this is my equation where we are considering savings as the dependent variable and it is regressed on income. So, we are trying to find out whether savings are impacted by incomes of individuals or not. So, this is an individual specific observation where we are saying that we are trying to find out whether income of individual I impacts his or her savings or not. And suppose variance of ui given income I is equal to sigma square income I. So, here in this case Hx is equals to x. Alternatively, I write it sigma square xi, right. So, the functional form of Hx is simply xi, okay. That is, the error variance is proportional to the level of income. As income increases, the error variance also increases proportionately, because sigma square here is a constant term. Now, we discussed the steps to obtain WLS estimate. The original equation is again given by this. Now, it is divided by root over hi. So, I stick to my previous example. If the form of variance is given as sigma square hi, then this is variance, as a result of which my standard deviation or standard deviation of the population error will be root over sigma square hi, that is sigma root over hi, right. Now, since sigma is constant, we are ideally dividing this equation by only root over hi. So, if I divide it by root over hi, then what happens? We have this expression. So, beta naught divided by root over hi, beta 1 xi 1 divided by root over hi, and so on. Because now variance of ui given xi is equal to sigma square hi, therefore, variance of ui divided by root over hi given xi is equal to sigma square, right, and that is why quite obvious, fair enough. So, if all Gauss Markov assumptions are fulfilled except for the one of homoscedasticity by the original model, then equation 3 satisfies all Gauss Markov assumptions, because our only problem was that our errors were not homoscedastic, errors were heteroscedastic. But if I write equation 3, if I write it in this form, knowing the form of heteroscedasticity, then you can see that the variance of this term, variance of ui given root over hi for conditional upon the values of xi is equals to sigma square. So, this is actually homoscedastic errors. So, if homoscedastic errors are there and other assumptions of Gauss Markov theorems have already been fulfilled, then we can estimate equation 3 using OLS, and then OLS would give us best linear unbiased estimators. So, we have the more efficient or the most efficient estimators, the best estimators, along with the fact that the estimators will also be unbiased, right. But one thing we need to notice here, and that is the variables are not now x1, x2 and so on. Instead, what are the variables? The variables are now xi 1 upon root over hi, similarly xi 2 upon root over hi and xik upon root over hi, and also in place of the constant term we have one variable which is 1 upon root over hi, right. So, we rewrite equation 3 as yi star equals beta naught x I naught star plus beta 1 x I 1 star and so on, plus beta k x I k star plus u I star. However, these estimators will be different from OLS estimators, because as you can see that our variables have changed. So, if our variables have changed, then of course, the estimated parameters would also change, and let us denote these estimated parameters or rather parameters as beta naught star, beta 1 star to beta k star, and they are the GLS estimators. They could be different from OLS estimators. The GLS estimators for correcting heteroscedasticity is called WLS estimators. They are called WLS because beta I star minimizes the weighted sum of squared residuals where each squared residual is weighted by 1 divided by HI. So, if you remember earlier when we talked about OLS, beta j hat was designed to minimize the sum of square residuals and we did not use any weights there. But here in case in this context, what we are minimizing? We are minimizing summation ui square, ui star square, and ui star square is actually summation ui divided by root over hi and the entire thing square. So, here in this context these individual observations are weighted by this factor which is 1 divided by hi, and as a result of which beta I star minimizes the weighted sum of squared residuals, where each squared residual is weighted by 1 divided by hi. So, algebraically beta j hat minimizes summation I equals 1 to n y I minus beta naught minus beta 1 x I 1. So, I write the original model and then the entire thing divided by hi, because for each and every variable it is divided by hi root over hi, and when I go for squaring the entire expression or I have squared here, then basically this is hi in the denominator. So, that is why we have hi. The fact that each observation is divided by its square root of its population error variance implies that observations with smaller variances receive greater weights. Alternatively, the idea is to give less weight to observations with high error variance. So, observations that are in the combination of y and x, suppose there are only two variables, one y and one x, one dependent variable, another independent variable. Now, if we observe very high variance between y and x specific to a particular observation, then we would consider the quality of that observation to be poor compared to observations having lower variances, right, because lower variances implies that they are more close to the mean of the series, and the mean of the series is expected to represent the population expected value or population mean, as a result of which we can say that the quality of those observations having lower variances are actually higher or better. Now, in order to in this scheme of things, that is in weighted least square technique, what we are doing is that giving lower weights to the observations having higher dispersion or higher variances, because what we are doing is that taking aside the constant term, we are dividing each and every observation by 1 upon root over hi or 1 upon hi. Now, the thing is that since hi is a part of the error variance, the larger the error variance, the larger the denominator and the smaller is the weight. Alternatively, the smaller is the error variance corresponding to a particular observation, smaller is hi and larger is the weights associated with that observation. So, that is how we are actually going for an estimation where observations having higher variances are actually penalized by assigning lower weights to them, and better quality observations having lower dispersions or deviations from its mean value is actually provided or given higher weights in terms of 1 divided by root over hi. Then we talk about something called feasible GLS. So, this actually is applicable when you do not know the form of heteroscedasticity. So, most often the form of heteroscedasticity is not known. Nevertheless, we may model the function hxi and use the data to estimate hi denoted as hi hat. Use of hi hat in the GLS transformation is known as FGLS or feasible GLS. So, what exactly we are trying to do here is that we are trying to hypothesize the functional form of the relationship between the independent variable and the error variance. So, the relationship between independent variables and the error variance is given by hxi or hi, and on that basis of that hypothesized relationship, we try to find out whether such relationship actually exists or not, and if we observe that relationship actually exists, then we incorporate that relationship. So, feasible GLS actually goes one step further and first tries to estimate the relationship between the error variance and the independent variables. So, suppose the variance of Ux is given as this. So, this is a nonlinear functional form and therefore, Hx. So, we have this constant component here and the rest of the component is denoted as Hx. So, Hx is exponential delta naught plus delta 1 x1 and so on plus delta k xk. A nonlinear functional form is easy to use when correcting for heteroscedasticity, and it must ensure that Hx is greater than 0. This is the same condition which we required earlier also, because error variances has to be 0 and as a result of which Hx has to be greater than 0 provided sigma square is always greater than 0. Equation 4 can be written as u square equals to sigma square expected delta naught plus delta 1 x1 and so on plus delta k xk multiplied by, we introduce v where v is the error term. What is done is that instead of having this variance of u given x, we are considering u square, because you know that variance of u given x is actually expected value of u square, and then by taking out of the expectation operation, we are introducing a random error term here which is v. Now, once it is done, it takes an estimable form and it can also be converted into a linear functional form which could be estimated using WLS method. So, we write by taking logarithm, natural logarithm on both sides, we write it as logarithm of u square equals logarithm of sigma square, and then exponential of this entire expression comes as it is and exponential is removed, plus we have logarithm of the error term which is log of v. Alternatively, I write it as logarithm of alpha naught plus delta 1 x1 plus delta 2 x2 plus delta k xk plus e. Now, you can see that I think I have missed out one delta naught here. So, alpha naught is actually delta naught plus logarithm of sigma square. So, these two terms are included in alpha naught and the rest of the things are as it is, and logarithm of v is denoted by e, where expected value of e is equals to 0 and covariance between e and x is also equals to 0. These are required as part of our classical linear regression model assumptions, right, CLRM assumptions. But if all Gauss-Markov assumptions are fulfilled, then OLS estimates of equation 5 will return unbiased estimates of delta j, that is j running from 1 to k. But the problem is that u square is not observable. Therefore, we first run a regression of logarithm of u hat square on x1 x2 to xk, where u hat is obtained from the regression of y on x1 x2 to xk. So, first of all, we go back to the original model, run a regression of y on x1 x2 to xk, collect the residuals, that is u hat, then run a regression of u hat on x1 x2 to xk. Okay. Then the fitted value is obtained as g hat equals alpha naught plus delta 1 hat x1 plus delta 2 hat x2 and so on up to delta hat k xk. Now, you can see that my original equation was logarithm of u hat square equals to this expression. Now, when we talk about the fitted value, then fitted value actually considers only this portion, and suppose we denote it by g hat, right. So, g hat is the fitted value, hence h hat is exponential g hat. If you remember, h was actually an exponential function of the, originally this was my hx, exponential of this value. Now, I have fitted values of this component except for delta 1, delta naught. In place of delta naught, I have alpha naught, which is basically delta naught plus logarithm of sigma square. So, there are slight differences, but broadly I can consider it to be exponential g hat. Then we estimate the equation y I star equals beta naught x I star plus beta 1 x I star and so on plus beta k x I k star plus u I star using WLS, where the start variables are weighted by 1 upon root over h I hat. So, once I have estimates of h hat and there are n observations. So, individual specific observations are denoted by h hat 1, h hat 2 and so on. So, we are dividing each observation by root over h I hat. So, this is very similar to WLS, again we are using weights. In case of feasible GLS, what has been done which is different from WLS is that we do not know the functional form, or rather we have hypothesized a functional form of the error variance with respect to the independent variables, and then we have tried to come up with an estimate of the hypothesized relationship. The estimate of the hypothesized relationship is given by g hat or h hat equals to exponential g hat, and then we divide the original equation by that estimated value of the hypothesized relationship, and then we try to obtain the values of beta naught, beta 1, beta k. Now, you can see that if the error variance is not dependent on the independent variable, which is which alternatively mean that there is no heteroscedasticity, then delta 1 to delta k will be equals to 0. So, in case we have a null hypothesis which says that delta 1 equals delta 2 to delta k equals to 0, this null hypothesis will not be rejected, and if this is not rejected, then this means this functional specification that actually has two alternative implications. First of all, this kind of a linear functional specification or this kind of a nonlinear functional specification is actually not valid. So, this relationship does not exist. Alternatively, it can also mean that the error variance is actually non heteroscedastic. So, it is homoscedastic, and in that case of course, we do not need to apply or go for a WLS, but if all or some of the delta 1 to delta k turns out to be non-zero statistically, then we can go for this kind of an FGLS or feasible GLS, where we divide the original variables by root over h I hat, the estimated hypothesized functional form, and then obtain the values of beta naught, beta 1 to beta k. Again, this beta 1, beta 2 to beta k are not equivalent to the OLS estimators or OLS estimates, because you would see that again our variables are not what we have observed in case of OLS or what we would have used in case of OLS. The variables have changed, which has already been discussed. So, since FGLS obtains HI hat from the same data, it is actually blue. The estimators are biased but consistent and more efficient than the OLS estimators. So, what we actually we call it biased, the reason is that this beta naught or whatever we estimate, suppose the estimated values are denoted by or estimated parameters are denoted by beta naught star, beta 1 star and so on, beta k star hat, and they are not equal to beta naught, they are not equal to beta 1, they are not equal to beta k, as a result of which we cannot call them unbiased estimators if the population parameters are actually beta naught, beta 1 and beta k, right. And that is why the estimators are biased, but we can easily prove that they still are consistent, which is a large sample property and they are more efficient. So, consistency is there the long we assume that the covariance between x and u or the covariance between these variables and ui star is equal to 0. The estimators are consistent and they are more efficient than the OLS estimators. So, that brings me to the end of the discussion on heteroscedasticity. We have discussed different perspectives, that is its definitions, detections, as well as how to deal with or how to correct for heteroscedasticity. These are the references. Thank you.